Hello everyone. In this video we are going to see topic modeling using sentence transformers. A big shout out to Martin for the bird topic library from where most of the concepts that we discussed today are taken. First of all, before even moving ahead with the algorithms etc., let's understand what topic modeling is. Let's say you have a collection of documents and you want to identify different topics or genres that are present in the documents. So it is impossible to go through the documents manually and then segregate them into different topics. So that's why we use natural language processing techniques to do topic modeling automatically. So topic modeling helps you to understand the main themes, topics or genres that are present in the collection of the documents. In order to understand better, let's take the dataset of Hollywood movie plots that came out in the last 15 years. Let's assume that we have about 3000 movie plots. So the first thing is, how do you automatically identify different themes or topics within these movie plots? For example, if you want to automatically classify any given movie into a genre, how do you do that automatically? That's where topic modeling comes into play. And the second thing is, if there is a new movie plot, how do you automatically label or classify that movie plot into a given topic? So the important thing to realize is that, let's say if we already had predefined labels, that is all the movie plots were already tagged with their genres, what we could do is just train a multi-class or multi-label classifier to predict the genre of a given new movie. But here we don't have any predefined labels or tags for our movies, so we are going to automatically identify the topics from our movies, and those topics will be the genres for us. So in a supervised setting, you already have label data, which is every movie and its corresponding genre, and you train a model, and any new movie plot you run through the model to identify the genre automatically using the trained model. But in unsupervised setting where you don't have labeled data, that's where topic modeling comes into play, and we can identify the topics or themes automatically. In one sentence, let's understand what multi-label or multi-class classification is. If you take a given movie plot and assign it one theme or one topic, let's say for example from adventure, horror, thriller, romance, comedy, etc. If you just pick one class to be associated to the movie plot, that's multi-class classification. But for example, for the same movie plot, you want to tag with multiple labels, let's say horror, adventure, thriller, etc. If you want to give multiple labels to a given movie plot, that is called as multi-label classification. It's not really important for our topic modeling use case, but just letting you know so that we understand that. So let's define our goal for the movie plots. Our goal is to identify different themes, that is topics or genres among the movie plots, and categorize them into those different themes. Those themes could be, let's say, romance, thriller, adventure, comedy, etc. So among all the 3000 movie plots that we have, we want to automatically identify and group movies into different genres. That's what we are trying to do with topic modeling. Now the agenda for this video is to discuss how we do topic modeling with sentence transformers, that is using document vectors or sentence vectors. So the first thing is, we'll convert each document, in our case movie plot, into a vector using SBERT library. Then we'll reduce the dimensions of each movie plot using UMAP algorithm. So it's a dimensionality reduction algorithm, just like PCA, T-SNE. UMAP is sometimes more superior version of PCA and T-SNE. Then you will use clustering algorithms like HDB scan or k-means to cluster all these movie plots into some n clusters. Then from each of those clusters we'll extract the top keywords, because we need to identify what's the main topic or theme for each cluster, and we can only do that if we find the top keywords from there and then attach a topic to it. And the fifth point is we are going to discuss different improvements to this baseline algorithm. So this baseline algorithm is taken from bird topic library, and we'll see how we can improve this baseline algorithm with some interesting techniques. So let's first understand what's step 1 of topic modeling. So it is essentially converting each document into a vector of fixed dimensions. So in our case, we are converting each movie plot into a fixed size vector using the sentence transformers, that is SBERT library. And the main thing is we do it for all the documents that we have. We are going to convert all the movie plots individually into their own fixed size vectors of, let's say, 384 dimensions. So at the end of the day, you have 3000 vectors of 384 dimensions, and each vector corresponds to a movie plot. Now the next thing that we are going to do is cluster the movie plots. How we can cluster them is, because now we have this 384 dimensional vector and we have 3000 of those, we can cluster them automatically using algorithms like k-means or HDB scan. So with k-means, we need to give the number of clusters that we want, which is k, and it also doesn't support outliers. What that means is that among all the 3000 movie plots, every movie plot has to belong to one particular cluster among the k clusters that we define. And since k-means works on cosine similarity, we can use the full-sized vectors, that is, we can directly operate on the 384 dimensions that we have. But k-means has some cons, as you can see, because you need to give the number of clusters. So we need to know how many topics or themes that we have beforehand in order to give this fixed k. It could be like 10 topics or 20 topics, so k could be 10 or 20. And sometimes it's not ideal, since we don't know the distribution. If we are trying to give an automatic k ourselves, we could go wrong. So in order to counter that, we have HDB scan algorithm, where you don't need to give the number of clusters beforehand, but you just need to give some hyperparameters, the cluster distance and other things, and it will automatically identify the number of clusters for you. And the beauty with HDB scan is that it can create a separate cluster where it can put all the outliers. So if any of the points are very diverse from each other, they need not be put into a single cluster, and all of those diverse points could be put into a different outlier cluster. But for HDB scan, you need to lower the dimensions from 384 to a lower dimensions, because HDB scan can operate computationally on lower dimensions, as well as in order to group them together, it's more effective if you have a lower dimensional number, for example, let's say 5. So what you need to do is you need to convert these 384 dimensional vectors into a lower dimensional vector of length, let's say 5, using dimensionality reduction algorithms like UMAP, T-SNE or PCA, etc. One disadvantage with HDB scan is that since we can't control how many will go into outliers, a large number of points could be placed into outliers as well. Anyways, As we have seen, we have clustered the documents, in our case movie plots, into some fixed number of clusters, and perhaps one distribution could look like this, as we have in the image, where each color represents one cluster. Now the next step that we have is to identify the keywords within each cluster. Let's say, for example, we have 10 clusters from either k-means or HDB scan algorithm, and each cluster would contain a fixed number of movies. In our case, let's say cluster 1 might have The Notebook, 50 First Dates, Crazy Stupid Love, all these movies, and cluster 10 could be The Ring, The Conjuring, etc. Now our goal is that we automatically identify the content of this cluster, and we should be able to tag that into the genre that it belongs or the topic that it belongs to, in this case romance. And similarly for cluster 10, we perhaps want to identify automatically that the movies or the documents that are present in cluster 10 represent to horror. So that's our goal. And how do we achieve that goal? So in order to do that, first we need to identify what's the text that is present in each cluster, and from the text we should be able to extract top keywords or important words, because only when we look at important words, then we can automatically give a topic or genre to that cluster. So what we'll do is we'll use the TF-IDF algorithm, and here we are doing class TF-IDF. I'll explain what that means. So essentially we have 10 clusters in this case, and cluster 1 will be a collection of, let's say, 50 movies, and similarly cluster 2, and then let's say cluster 10 is a collection of 83 movies, and you will see that all the 3000 movies will be distributed in these 10 clusters. And cluster 1 text would be just a concatenation of the whole text of these 50 movie plots. So cluster 1 text is just movie plot 1, that is the Notebook's movie plot, combined with 50 First Days movie plot, combined with Crazy Stupid Love movie plot, and similarly we just append all the 50 movie plots together and we get the text of cluster 1. Similarly, cluster 10 mostly represents horror, so we are going to get the movie plot of The Ring and then The Conjuring, and we are just going to append all the 83 movie plots together and create one single long text. And what we are going to do is, our goal is to identify the top keywords within each cluster. Since we have the text that is the concatenation of all the movie plots, we can use TF-IDF among the clusters itself to identify the top keywords. And why does TF-IDF work? So TF-IDF captures this idea that a given word has high TF-IDF score if it's very frequent in this cluster and it is rare across other clusters. So in cluster 1 text, each word will have a TF-IDF score, and if we just get the top words that have the highest TF-IDF scores, let's say top 10 words, then those are the top 10 keywords for this cluster. And inherently, because of the way TF-IDF is calculated, we are going to extract keywords that are very frequent in cluster 1 but that are rare across other clusters. So for example, let's say we extract top n keywords, and for cluster 1 those n keywords could be love, enraged, wedding, relationship, etc. Since cluster 1 is a collection of romantic movie plots, we might get these as the top keywords. And then what we need to do is manually assign from a given set of genres. Let's say We have already created 10 or 15 genres that we might encounter, like action, adventure, romance, horror, etc. Then we can just assign one topic to that cluster after looking at the top n keywords. In this case, cluster 1 would be manually assigned with romance as the topic, and cluster 10 will have dead, killed, murder, devil, etc. So we are going to manually assign horror as the topic for that cluster. So assigning a topic label or genre to each cluster is what we do in step 4. And just carrying that over, what happens is that now you'll have the same set of clusters and you'll identify the top n keywords from each cluster, but now instead of those keywords you'll replace that with a topic or genre. In our case, for example, action, comedy, Indian, etc. So at the end of the day, we started with 3000 movie plots. We automatically formed clusters from those movie plots, and for each cluster we have assigned a topic label. And now for each of the 3000 movie plots that we have a fixed topic label or genre, because each of the movie plot belongs to a cluster and that cluster is assigned a label like action, comedy, etc. Now the beauty is that you can get any new movie plot or data point, and let's say you have 10 clusters, you can store the centroid of each cluster, and for any given new movie plot you can convert that into a vector and see which among these 10 clusters is it closest to, and give the same label as the cluster that it is closest to. Or you can do some kind of soft clustering even. Now let's discuss some interesting improvements that we can do to the discussed algorithm. For example, we extract these words love, enraged, wedding, relationship for cluster 1 as the top n words, and looking at those top n words we are assigning a genre from a given list of genres that we already have. Now that's done manually, but what we can do is you can convert the same thing into a GPT-3 prompt, where the prompt could just look like this: the words love, enraged, wedding, relationship belong to one of the following categories, and you give all your predefined list of categories here. The category is, and you just prompt with this, and GPT-3 will output romance or whatever is ideal to these keywords from the list that you already have. So converting top keywords of every cluster and mapping it to a topic or genre, you can automate that with GPT-3 or any large language model with a prompt like this. And second improvement is actually replacing named entities in plots before vectorizing them in order to get high quality vectors. Let's understand why we need to do this. The issue is that when, let's say, you're converting a movie plot, let's say interstellar movie plot, into a vector of 384 dimensions, this vector is heavily influenced by the named entities that are present in the original text. For example, Cooper, NASA, Donald, not just names, but it could be company names or places, other things. Those heavily influence the vector that you get using sentence transformers. But the problem here is that if you are trying to cluster movie plots to identify the genre that it has, for example adventure, action, romance, etc., these names and places don't contribute much to that. So if our goal is to cluster the movie plots based on their genres, then the named entities like proper nouns or place names or locations, company names that you have don't contribute much to the final vector, right? The adjectives, verbs or common nouns that you have might contribute more to the final vector if you are trying to cluster based on genres. So what you can do smartly is to replace named entities with some generalized versions of it. For example, you can replace Cooper with person 1, and similarly NASA with company 1, Donald with person 2, etc. So if you replace named entities, their generalized form, then the vector that you might get out of it will be more suitable to cluster based on the genres. So improvement 2 could be replacing named entities with their generalized alternatives so that the vector that you extract will be of better quality and not influenced by these named entities. Now coming to improvement 3, so we have seen that we are taking class TF-IDF, and within each cluster we are accumulating all the text of the corresponding movie plots that belong to that cluster, and we are taking TF-IDF. So if you go back, you will see that cluster 1 is a collection of all the text of 50 movie plots of the notebook, 50 first dates and everything. Now we have the same problem here, which is if you are trying to extract keywords using TF-IDF, and depending on your task here we are trying to identify the genre of the movie plots, then most of these nouns like Cooper, NASA, Donald, all these proper nouns might not make more sense, just like we discussed previously. So what you can do is, when you are appending the text of all the movie plots, instead of appending the full text of the movie plot, you can keep only verbs and adjectives and then append all the verbs and adjectives of a given movie plot with another. So what you can do is you can transform this movie plot. Instead of using the movie plot, just use the verbs and adjectives that are present in the movie plot. If your goal is identifying the genre, then verbs and adjectives might contain more relevance to you than just words like Cooper, NASA, Donald. So what we can do instead is, instead of using this movie plot, we can use spacey, etc., and just run a parts of speech tagger and convert this movie plot to just keep only the verbs and adjectives from the movie plot. So for example, from this movie plot we can just keep threatened, widowed, those are the verbs, and farmer, teen are the adjectives. And the beauty is that since TF-IDF doesn't take into picture the order of words, etc., even if you just keep verbs and adjectives like this and add all the movie plots with just verbs and adjectives extracted from them, still TF-IDF will help in identifying the top keywords, in our case verbs and adjectives. Because what happens is that instead of using the plot of the notebook, we are just going to use the verbs and adjectives from the notebook movie plot. Similarly, we are going to append the verbs and adjectives that we saw in 51st dates. So this text will be just verbs and adjectives from all the 50 movie plots. Similarly, cluster 10 will be the same. So simply put, instead of extracting nouns, Cooper and other things, you can just extract just the verbs and adjectives, or depending on your use case, what you want to tag as, identify that parts of speech, etc. And then you can use those as the top n keywords. So that is improvement 3. Filter the movie plot to keep only things that you want. In our case, it could be verbs and adjectives, or you can just keep only common nouns, whatever be the case. Depending on what you want to classify your topics on, you can filter this document to keep only the necessary words that are relevant to your topic modeling use case. So just to recap everything, we have seen how we can do topic modeling using sentence transformers. First, what we did was to convert all the documents that we have into vectors. Then we have applied clustering on those vectors in order to group all the different movie plots into different groups. And from each group, that is each cluster, we tried to identify the top keywords of the cluster by using class TF-IDF, that is using TF-IDF within the clusters. And once we identify the top keywords in each cluster, we map that into a fixed topic or genre, for example romance here. Similarly, each cluster is assigned to a fixed topic or genre, and any new movie plot could be compared with the closest clusters and can be assigned the topic label of that cluster. And we have also seen how we can do some improvements. The first improvements is automatically mapping the top n keywords into a genre or topic. Second is how do we better the quality of the vector that we extract from each document in order to better suit the topic modeling objective that we have. And the third improvement was how do we extract better keywords, again fitting with the final objective of our topic modeling, which is identifying genres. So if you want to identify genre of a movie plot, we don't need to consider the whole document, but rather a filtered subset of the document. That's what we have seen. Hope you have learned how we can do topic modeling using sentence vectors, and also learned about some interesting improvements that we can do depending on the goal that we have. Thanks for watching.